Welcome to The Explainer. Today, we're tackling what is honestly one of the most terrifying flaws in modern artificial intelligence, and we're going to do it methodically, step by step. Standard neural networks, the point estimate models running behind the scenes of practically everything today, have a massive, fatal flaw. They are fundamentally overconfident. When you deploy these in safety-critical systems, like autonomous driving or medical imaging for cancer screening, a model making a catastrophic error with 99% confidence isn't just a bug, it's an absolute disaster. So today, we're going to engineer a solution to this from the ground up, diving into the rigorous, mathematically beautiful world of Bayesian neural networks.
Think of me as your senior architect for robust AI. Here's our blueprint for today. We'll start with the confident idiot problem, move into mapping epistemic uncertainty, visualizing the weight cloud, and approximating the true posterior. Then we'll tackle the reparameterization trick, and finally, look at engineering realities and alternatives.
All right, Section 1, the confident idiot problem. Standard AI on out-of-distribution data. Okay, let's dive into a classic scenario. Imagine a standard convolutional neural network gets fed an image of purely random, static pixel noise. It doesn't just fail, it outputs a 99% confidence that the static is a dog. It does this because its weights are rigid, fixed numbers. They literally have no mathematical mechanism to say, I don't know. But when a Bayesian neural network encounters that exact same noise, it essentially says, oh, this image is random noise, I'll increase my uncertainty and ask for a human. Its uncertainty spikes, it flags the anomaly and requests human intervention. And honestly, that is the exact behavior we absolutely need in a robust system.
Moving on to Section 2, Mapping Epistemic Uncertainty. Understanding, I don't know.
To build this capability, we need precise mathematical language. Now, there are two main types of uncertainty. Aleatoric uncertainty is just noise in the data itself. Think of a blurry camera lens. We aren't trying to solve that today. What we are rigorously defining here is epistemic uncertainty. This is uncertainty caused by a pure lack of knowledge or a lack of training data. When a model operates out of distribution, it has absolutely no reference points. Bayesian neural networks mathematically force the model to track this epistemic uncertainty, literally mapping out exactly what it doesn't know.
Section 3, visualizing the weight cloud, from point estimates to probability densities.
I want you to picture a standard one-dimensional line of network weights. Normally, these are just dots, right? Single point estimates. But in a Bayesian neural network, we replace every single dot with a Gaussian bell curve for every single weight. We start with a wide, flat bell curve. That's our prior. Then, as we observe training data, we move to our posterior approximation. You'll notice the bell curve's getting narrower and narrower. This is vital. In a Bayesian network, learning is literally the process of reducing the variance of your weight distribution. The model gets more certain as it sees more data.
And here is where that totally pays off. When you plot the predictions, you'll see that in areas with lots of training data, this cloud of possible weight combinations is incredibly thin. All the potential lines agree. But the exact second you feed the model out of distribution data, the prediction expands outward like a giant megaphone. The shaded uncertainty band just widens massively. This visual expansion is probability density mapping in action. It is quite literally the geometry of I don't know.
Section 4, Approximating the True Posterior. Bayes' theorem in deep learning.
Let's see how this builds our mathematical foundation. Back in the 1990s, researchers like Radford Neal proved that infinite-width neural networks with Bayesian priors work perfectly in theory. But here's the catch. Calculating the exact true posterior distribution of the weights using Bayes' theorem is a massive bottleneck. It requires integrating over millions of dimensions, which is completely intractable for modern deep learning. So, the rigorous solution we use today is variational inference. We basically guess the true posterior using a simpler, trackable distribution that we can actually optimize.
What's truly fascinating is how we optimize that guess using the evidence lower bound, or ELBO, loss function. It's essentially this mathematical tug-of-war where we balance two competing forces. On one side, we have the negative log likelihood, which forces the network to actually fit the data. On the other side is the KL divergence penalty, which acts as a regularizer. It's kind of like trying to pack for a flight, right? The negative log likelihood wants to stuff everything into the suitcase to perfectly match your data, while the KL divergence acts like the strict airline baggage limit, penalizing the network if the weight distribution's strayed too far from our prior. Without it, our standard deviations would absolutely explode.
That brings us to Section 5, the reparameterization trick, unblocking backpropagation.
Back in 2015, the Blundell breakthrough gave us the reparameterization trick.
And this brilliantly illustrates the sync between code and math. In the PyTorch implementation, you'll see the variables mu and rho. Now, these aren't just standard weights. They are the parameters of a distribution. Mathematically, W equals mu plus sigma times epsilon. We isolate the deterministic nodes, mu and sigma, from the random node, epsilon. Epsilon is just drawn from a standard normal distribution and treated as a constant input. And because of this clever separation, gradients can flow perfectly through mu and sigma during backpropagation.
Finally, Section 6, Engineering Realities and Alternatives, Scaling to Production.
Grounding all this brilliant theory in hardware reality, the costs are, frankly, immense. First off, your parameter memory footprint exactly doubles because every single weight matrix now needs both a mu matrix and a rho matrix. Furthermore, to get that uncertainty megaphone we talked about, you can't just do one forward pass. You have to draw S samples, which means compute scales linearly. If you do 10 forward passes, your compute increases 10x. This massive explosion in activation storage pushes large models like a standard Resonant 50 right off the edge of consumer GPU VRAM.
You also run into tricky training failure modes, with the most common being posterior collapse. If that KL divergence penalty we talked about earlier is too strong, the standard deviations of your weights will collapse to near zero. The model basically just becomes a standard deterministic network again. The rigorous engineering fix for this is KL annealing. You start training with the KL penalty at zero and then slowly scale it up over the first several epochs, letting the data likelihood establish a really strong gradient signal first.
Because of these serious VRAM and compute bottlenecks, you won't see true BNNs powering massive 70 billion parameter large language models like GPT-4 anytime soon. The gradient noise and parameter doubling just make it economically unfeasible. Instead, the industry relies on deep ensembles. This is where you train 5 to 10 independent standard networks in parallel. Deep ensembles mathematically approximate Bayesian model averaging, and they capture that crucial between-mode uncertainty without the massive gradient noise of a true BNN. It's a very practical compromise.
So the crucial point is this final mental model. A standard neural network is like a single rigid bridge. It works great under normal conditions, but the exact moment out of distribution winds blow, it shatters because it has absolutely no flex. A Bayesian neural network, on the other hand, is like a suspension bridge made of thousands of independent springs. Where you have data, the springs are tight, but where you lack data, the springs wobble. And that wobble safely and reliably indicates your epistemic uncertainty.
Which leaves us with this final, critical thought. We've seen exactly how point estimate systems mathematically hallucinate confidence in the face of the unknown. And we've seen how probability density mapping fixes it. So ask yourself, if the model architecture you are deploying today completely lacks the mathematical vocabulary to express epistemic uncertainty, can you truly trust it to drive a car, diagnose a patient, or make any safety-critical decision? Thank you so much for joining me on this explainer. Keep engineering robustly, and I'll see you next time.